Okay, so today, as we told, we will be starting with the complete design of simply supported beams as well as cantilever beams. So we will start with simply supported beam. So I have told you to go through some clauses in the code. I hope you have done that from your side. Anyway, basically, first of all, we have to see some specific definitions given in your IS 456. So these things are actually needed for doing the actual design. So that is the reason why I have told you to go through this. So let's see what we have in that. So first one is regarding your effective span, and I am assuming that you already know what do you mean by effective span. You have learned this from your mechanics of solids. So anyway, we need not spend much time on that. So the details regarding this, that is how to take the effective span, is actually given in page number 34 of your IS 456. It's in clause number 22.2. So let's see what we have. The clause actually gives the details of how you can take the effective span for your analysis and design. Okay, so in design of concrete structures, basically sometimes you will be in need of calculating the total load acting on the structure. Sometimes we will be knowing the load which is acting on the beam, and we may be in need of converting that to moments, and sometimes we will be in need of taking up the critical sections for bending moment as well as shear force, I mean design of shear. So in such cases we need the value of effective span. So the first thing is that how to take the effective span. So for that, your IS 456 actually give you some guidelines. So let's see what is mentioned here. So if you go through this clause, so it is mentioned like, unless, I think you can see this PDF, right? You are able to see this.
Yes, sir.
Zoom it in. The zoom level is right. Okay, no?
Yes, sir.
Okay then. So unless otherwise specified, the effective span of a member shall be as follows. So it gives some conditions. So first condition, in condition number A, it is mentioned for simply supported beams or slabs. In both cases, this is acceptable. So when we perform the design for slab also, we will be referring the same clause. So as per this clause, the effective span of a member that is not built integrally with its supports shall be taken as clear span plus the effective depth of slab or beam or center to center of the support. So there are two conditions actually. So it is to be taken as the clear span. What do you mean by clear span? So right now you will be in a position to tell me about that. What do you mean by clear span? Let's keep one more thing here. See, suppose we are considering the side view of a beam which is supported on 2 walls. Okay, like this. So let's assume we have 2 walls here on which this beam is actually supported. So let me mark it here. Let's assume that is a brick wall. Anyway, so the clear span means it is actually the distance from the surface of this support to this support. So basically this will be your clear span. So this much distance will be your clear span. Okay, so this is your clear span. Now what is mentioned here in this code? It is mentioned that it shall be taken as clear span plus the effective depth. That is your first condition. So basically first what you have to do is that you have to add up this clear span plus effective depth, that is small d. So basically your effective span, say let's mark it as small letter L, effective, will be equal to clear span plus d, or we have one more condition, that is clear span plus effective depth of slab or beam or center to center of the supports. That is, the second condition is like this. It can be the distance from the center of this support to center of your second support. So we have 2 values now. In these 2 values, which one should be taken? It is the smallest of these 2 values, whichever is less. So basically in this case, what you have to do is that you have to also calculate the center to C by C distance between your supports. Okay, So, and you just have to compare this value and you have to take up the smaller value. In this, you have to take the smaller value. So that will be your effective span for all the remaining analysis as well as design. That will constitute your effective span. So that is what is mentioned in your first clause. The second part, that is B part, actually deals about continuous beams. So right now we won't be dealing with the continuous beam. We will be mainly dealing with simply supported beams. So, but let's have a look onto this. What will happen when we move on to continuous beams or slabs? So what do you mean by a continuous beam? First of all, let me see whether you know that. What is a continuous
spans?
I didn't get it.
It has
It will be having
spans, like
okay. It will be actually spanning over more than 2 supports, right?
Yeah.
So it will be having multiple number of spans, right? Very good. So in the case of continuous beams of slabs, what we have to do? If the width of the support is less than 1/12 of the clear span, first of all, we have to calculate this. What will be the value equivalent to 1/12 of the clear span? And if that width is actually less than this quantity, the effective span shall be as in clause number 22.2a. That is what we have just now seen. So here in 22.2 clause number A, we have seen something, that is the effective span will be the smaller of center to center distance as well as clear span plus effective depth. So same thing applies to that. When in the case of continuous beams or slab, if width of the support is actually less than 1/12 of the clear span, we can go with the same condition. Else, what should be done? If the supports are wider than 1/12 of clear span or 600 millimeters, whichever is less. Okay, so here also you have to note, we need to compare two conditions, that is the width is larger than 1/12 of the clear span or 600 mm. In this, actually you have to take the smaller value. If it is wider than that, what should be done? The effective span shall be as under. We are provided with 3 more conditions. In the first case, we have for end span with one end fixed and other end continuous. I think it will be better if you can read this out. So otherwise it will be very boring, right? So basically in this code, what you have to understand is that for each and every condition, they have actually provided different clauses describing about how to calculate these things. So the main thing that we require is actually as discussed in this case. So because we will be dealing with simply supported beams here in this module, so we need to calculate the effective span of the member like this. First of all, you have to get the clear span, then you have to add up this clear span with the effective depth. That will constitute one value. Then you have to also calculate the center to center distance also. Then finally you have to compare these two values and take the smaller one and report that as your effective span. Okay. So regarding cantilever, also it is given the effective length of cantilever shall be taken as the length to the face of the support plus half the effective depth. Okay, so some conditions are given for cantilever beams also. Anyway, we will come back to this clause, at least for this clause number C, when we actually perform the design for cantilever. Okay, also in the case of frames also some clause is given here. So you have to understand that we have some clause in IS 456 and this is clause number 22.2, based on which we can find out the value of effective span. Okay, any doubts in this? No. Okay, so let's move on to the second thing. So the second point I have mentioned here is for control of deflection, you have to refer clause number 23.2 of page number 37 in IS 456. Okay, let's see what we have there. So here you have a clause mentioning about control of deflection. Why we should care about this thing, control of deflection? So as we are right now dealing with limit state of design, and the main specialty of limit state of design is that we will be considering the collapse at ultimate load by considering at ultimate strength by considering a ultimate load, right? And we will be also taking care of the serviceability condition at the working load. So basically we have to satisfy the serviceability requirements also, and deflection is one of the serviceability requirements. So we all know when we sit in a room, if the beam sit there, right? So as a designer, we should ensure that the deflection is not exceeding some condition, and we have direct procedure for calculating the amount of deflection that can occur in a beam. Those things we will deal in a later stage. For the time being, what the code suggests is that if you are starting by taking some assumptions, we will be automatically satisfying the deflection criteria. That is, when we fix the dimensions of the beam. So in the initial stage of the design, what we do is that we will be fixing the dimensions. So while fixing that, if you are following some set of instructions, the deflection condition will be automatically satisfied. That is what the code is actually suggesting to you. So again, I am again repeating, if when you design a beam, when you finalize the dimensions, if you are following some conditions, the deflection criteria will be automatically satisfied. So for that, what are the conditions? That is what is given in this clause. Okay, so let's go through that. The deflection of a structure or part thereof shall not adversely affect the appearance or efficiency of the structure or finishes or partition. The deflection shall generally be limited to the following condition, that is regarding the maximum permitted deflection. So we actually permit some sort of deflection which is not making much problem. So what is that final limit? Okay, so let's see that the final deflection due to all loads, including the effect of temperature, creep and shrinkage, and measured from the as cast level of the support of the floors, roofs or all other horizontal members should not exceed span by 250. So what you have to do is that if you are actually calculating the deflection using some procedure, we have some procedure again given in this same code itself. If you are calculating using that and you want to compare with the maximum permitted deflection, this is the correct condition. That is, first of all, you have to calculate about span by 250 and compare with that quantity. And one more thing is that if the deflection including the effect of temperature, creep, shrinkage occur after the erection of partitions, please note, after the erection of partition and the application of finishes. So basically we will be constructing the beams and columns first. After that we can calculate span by 250, or after completing the entire construction, that is we will be casting and constructing the beams, columns, then we will be constructing the partitions, then we will be applying the floor finishes and other finishes. Okay, once that is the case, after erection of partition and the application of finishes, it should not exceed span by 350 or 20 mm, whichever is less. Okay, you can calculate the value of span by 350 and you have to also compare with 20 mm. So suppose your span by 350 is coming around 21 mm. You should not consider that value. Instead, you have to consider this 20 mm. You have to compare the final actual deflection with this 20 mm and ensure that the final deflection is below this 20 mm. Is there any confusion in this? So let me be. Please give some response. Is this clear to you? So in this part, please note what you are actually doing is that you are actually taking up some procedure. Say, suppose I have a beam and I know the load which will be acting on that structure, and I also know the final dimensions of the structure and the amount of steel provided in that. And finally, I am just calculating the deflection which can occur in this beam by some procedure, and I will be obtaining it as, say, something like maybe 2 mm or say 5 mm. The total deflection that can come into picture is 5 mm. Once I get that value, what I should do? If the case, first of all, I have to check whether the partitions are also erected or not, and in the case or whether the partitions are already erected. So if that is the case, what I should do is that I have to calculate the value of span by 350 and also consider this 20 mm. Then I have to compare the obtained deflection using the procedure with these two quantities or the lesser one of these two quantities, and I have to ensure that the total deflection I obtained is actually less than this value. So, and again, please note, for your competitive examinations, Viva, interview and all, this is a question which is normally repeated. So basically they will be asking what is the maximum permitted deflection in the case of a beam. So in that case, what you have to tell is it will be span by 250 in this particular case, and if the case is like we have partitions and other finishes, it should be the lesser of span by 350 or 20 mm. Okay, so please note this. This is a question that you can expect for competitive examinations and this interview type questions and all. Okay, now moving on to the next part. So as I told earlier, if we are actually designing by following some specific procedure, these conditions will be automatically satisfied. So let's see what that is. So basically the vertical deflection limits may generally be assumed to be satisfied provided that the span to depth ratio are not greater than the value obtained as below. So basically what we have to consider is the span to depth ratio. So the basic value of span to effective depth ratio, please note the basic value of span to effective depth ratio for span up to 10 meters. Okay, so this condition is actually possible for spans up to a limit of 10 meters. So up to, if the beam is having a span of less than 10 meters, what you can do for cantilever, the span to effective depth ratio should be taken as 7. So basically we will be having L by D ratio. So basically span to effective depth ratio should be, if it is a cantilever, it should be 7. So basically at this particular stage in the starting of the design, we won't be knowing the value of our D. So what we will do is that based on the span, we will be actually calculating the D like this. And we will be using this effective depth for our design. So that finally, when we finalize the dimension, the condition of deflection will be automatically satisfied. And this is the case of a cantilever beam. Okay, so the L by D ratio must be equal to 7 in the case of a cantilever beam. And if it is a simply supported beam, the L by D ratio must be equal to another value, that is 20. And if it is a continuous beam, again, the L by D ratio must be equal to 26. So these are the conditions when the span of the beam which we are considering is less than 10 meters. Is it clear?
Yes, sir.
Anyway, while doing the design, we will be again going through these things. Now let's see what will happen if the span is greater than 10 meters. So we cannot always have a beam which is having a span less than 10 meters. So for span above 10 meter, the values in this clause, that is clause number A, may be multiplied by 10 by span in meters, except for cantilevers, in which case deflection calculation should be made. So if our beam is a cantilever beam, we cannot directly get a value like this if the span is greater than 10 meter. If the cantilever is having a span of say 10.1 meter, what we have to do is that we have to actually work out the final deflection, then compare with the maximum permitted value and ensure that our final deflection is less than the maximum permitted value. If it is not a cantilever, we can adopt the second part. That is for span above 10 meter, the value in this clause, that is if it is a simply supported beam, L by D ratio is, in this clause it is given as 20. So what we have to do is that if say suppose I am having a span of 11 meters. Okay, so for span above 10 meter, the value in A may be multiplied by 10 divided by span in meters. So basically this 20 multiplied by 10 by your span, that is 11 meters. That should be taken as the L by D ratio. Okay, so if the span is greater, you have to actually work out this quantity, that is 10 by your actual span. Then you have to multiply that with respect to the corresponding value based on whether it is a simply supported beam or a continuous beam. Okay, so if it is a cantilever beam, again I am repeating that deflection should be calculated. Now we have some more clauses, that is depending on the area and the stress of steel. For tension reinforcement, the value in the A or B shall be modified by multiplying with the modified. Anyway, I am just not explaining about the clause number C and D right now. While doing the problem, we will come back here and we will do this. So otherwise it will be very confusing for you if I am just theoretically telling everything right now. Okay, so for the time being, you just understand. To start with, we require a L by D ratio. And based on whether it is a simply supported beam or a continuous beam, you have, and whether cantilever beam, you have these L by D ratios mentioned in this clause number 23.2.1a. If the span is less than 10 meter, if the span is greater than 10 meter, what you have to do is that you have to again take up these values, then multiply the respective values by 10 by your span, actual span. Okay, I hope it is clear to you. That is regarding these clauses. Now moving on to the details of reinforcements. Let's see what we have here in clause number 26.5.1. That is regarding the maximum and minimum amount of reinforcement and other things. So 26.5.1. So basically 26.5 is giving details about requirement of reinforcement for structural member. In that we have beams, we have columns, we have slabs, and separate divisions is given for everything. So in this, the first subclause is 26.5.1, which deals about beams. Okay, in the beams, again, we know that we will be having tension reinforcement. In the case of doubly reinforced beams, we will be having compression reinforcement and other things. So in the again another subclause, that is 26.5.1.1. We have details regarding tension reinforcement. That is the details regarding the reinforcement which we provide in the tension zone. Okay, so let's see what they have mentioned there very fastly. So in the first clause, they are telling about the minimum amount of reinforcement. So I hope we have already checked this. I am not remembering. Anyway, let's see what is the minimum amount of reinforcement required. So the minimum area of tension reinforcement shall be not less than that given by the following equation. I hope you already remember this equation. So basically the thing is, like, in the tension zone, we need a minimum amount of reinforcement. So in the first module, we have actually just worked out what will be the amount of steel reinforcement that is required, but that is not the case. I might have mentioned there are a lot of conditions that should be satisfied. So in the actual design, what we will do is that we will just work out and find out what is the amount of reinforcement required for safely taking up the external load. Then we have to compare with the minimum amount of reinforcement suggested by the code. Also, we have to compare that with the maximum amount of reinforcement that can be provided in the beam. So these are two conditions. Once we finalize our design, we have to ensure that we are providing this minimum amount of reinforcement, and we have to also ensure that our reinforcement which we have right now provided is not greater than the maximum permitted amount. Okay, so for that we have two clauses, and this clause actually gives about the minimum AST that should be provided. So based on the width and the dimensions as well as the grade of steel used, you can find out the value of AS, which is the minimum area of tension reinforcement, and you can compare this value with the final amount of AST that is provided in your beam. So that is one thing. Then regarding the maximum reinforcement, the maximum area of tension reinforcement shall not exceed 0.04 BD. Okay, so you have to calculate this, and you have to ensure that the amount of steel provided is not greater than this value also. And for your examination also, in point of your examination also, if you haven't performed these two checks, you will be using 1 or 2 marks. So basically these checks will be having some credits as per your scheme. Okay, so please note, once you complete your design, you have to actually compare the final AST with respect to the minimum amount of steel as suggested by IS 456 as well as the maximum amount of steel permitted by IS 456. So this is regarding the tension steel. Now similarly we have some requirement regarding the compression reinforcement. So basically the maximum area of compression reinforcement shall not again be greater than 0.04 BD in the case of beams. Okay, compression reinforcement in beam shall be enclosed by stirrups, and again this is a condition that should be satisfied. Once we have some compression reinforcement, it should be enclosed by stirrups for effective lateral restraint. Okay, lateral, sometimes load will be acting in the lateral direction. So in order to prevent that, in order to ensure that it will be staying safely, so basically you have to provide the stirrups and the arrangements of stirrups. For the arrangements of stirrups also we have some clauses given in this code. Anyway, right now you just note down this: the maximum area of compression reinforcement shall not exceed 0.04 BD, that is 4% of the total cross-sectional area. So the maximum permitted amount of steel is 4% for the case of beams. And again, please note, these are some repeated questions for your competitive examination. In most of the PSC and exams like that, this question gets repeated. It may be either for maximum amount of permitted steel in the case of beam, it may be sometimes in the case of column, sometimes in the case of slats, and likewise it may vary, but this type of questions are usually repetitively coming for your competitive examination. Sometimes it will be minimum, sometimes it will be maximum. So this is the thing, it is 4% in the case of beam. So please do remember that. Then we have side face reinforcement. Anyway, for the time being, it is not required. And if you are interested, you can go through these things. Then we have transverse reinforcements in the beam. Maximum spacing. So I think this thing we have checked, 0.75D or 300 millimeters, right? Can I get a response? Somewhere yes. We have, yeah. So again, this thing actually I have taken from this clause itself, that is maximum spacing of shear reinforcement. We have already performed the shear design and the maximum permitted shear reinforcement. Let's see what we have here. The maximum spacing of shear reinforcement measured along the axis of the member shall not exceed 0.75D for vertical stirrups and D for inclined stirrups at 45 degrees. So we have already seen that we have different provisions for providing shear reinforcement. It can be vertical, it can be inclined, and we can also utilize the bent up bars. So if you are providing it in the vertical direction, the maximum permitted spacing is 0.75d, and if you are providing it in the inclined direction, the maximum the distance is different, that is it should be d, where d is the effective depth of the section under consideration, and in no cases it shall the spacing shall exceed 300 millimeters. Again, we were checking both these conditions, 0.75d as well as 300, and this is the reason it is already mentioned in the code that we should not exceed the spacing which is calculated using both these cases, the smallest of these two. Okay, we have already calculated the minimum shear reinforcement that is required, and again the same equation is given under the details of reinforcement, that is clause number 26.5. So here basically you have all type of requirements regarding the reinforcement, whether it is in the case of beam, whether again in the case of beam, whether it is in the case of tension, it is in the compression, shear, torsion, or whatever things that can come into picture. The details are actually given in your code. This is basically our guidelines upon which we can easily perform our structural design. Okay, so if you are going down distribution of torsion reinforcement, so these things we will come back in a later module. Then we have regarding flanged T and L-shaped beams. Then also we have requirements regarding the slabs. What is the minimum reinforcement, maximum diameter permitted in the case of columns also. So these things we will come back to these clauses in a later stage. Anyway, so for the time being, you just understand that we have a clause 26.5 under which we have all the details regarding the minimum and maximum permitted reinforcement, whether it be in the case of beams, columns, slabs, or whatever it may be. We have the clauses giving the details of the same. So that is the importance of clause number 26.5. And I have mentioned one more thing. I think this thing you might have already gone through because this was actually given as an assignment for you, regarding the details regarding the curtailments of reinforcement, and these details were actually given in your IS 46 code itself, clause number 26.2.3. so let's see what we have there. Yes, so if you see here, curtailment of tension reinforcement in flexural member, this is what I have asked you to write. So for curtailment, the reinforcement shall exceed beam. I don't think the explanation is necessary here because you have already gone through this as part of your assignment, right? So this is the area where you have details regarding the curtailments. Now we have 5 more minutes. Anyway, for that time, what we will do is that we will roughly go through the overall procedure by which we can perform the actual design of a simply supported beam. Okay. Before that, is there any confusion or doubt till now what we have discussed? Should I explain any part any more time, or is it clear?
It's clear, sir.
It's clear. Okay, fine. So let's see what are the steps that we should follow for design. And please note again, there is no strict rule that you should follow this typical pattern itself. Again, in our class itself, I may be following a different step. This is one procedure by which you can perform the design. That's all. There is no strict rules in design. Only thing is that our final structure must be safe against the load. It must be safe in serviceable as far as serviceability is considered, and it should be economical. That's it. So let's see what are the different steps given here. The step 1, what we have to do is that based on the data given, we have to actually calculate the effective span, and based on this effective span, we can calculate the effective depth. How? Based on the clause that is based on your L/D ratio. As we have discussed in the control of deflection, we have some L/D ratio based on whether it is simply supported beam or other thing, and based on that you can just find out the value of effective depth, and based on this effective depth you can calculate the value of effective span. So for this L/D ratio, you can just take up the clear span, that is the total length of the beam, and you can take L/D ratio as the value. If it is simply supported beam having span less than 10 meter, it will be equal to 20. So you just take L/D is equal to 20, and from that you just calculate the value of effective depth. Once you get the value of effective depth, you just move on to the clause corresponding to effective span and find out effective span. How you were calculating effective span? It was the center to center distance or the clear span plus effective depth. Right now we have effective depth in our hand, so that we can easily find out the value of effective span. So once you get the effective span, you can find out the value of moment acting on the structure as well as the shear force acting on the critical sections. Right. Once we have effective span, we will be having the amount of load. Maybe it may be concentrated load, it may be UDL, it may be or some other couple or something else. Okay, so based on that, you can easily find out the critical bending moment and critical shear force once you have the effective span with you. So you just calculate that. Then you have to find out the limiting neutral axis. How to find the limiting neutral axis? Can someone tell me how to find the limiting neutral axis? No idea.
Have the value for X limit by D for given reinforcements.
Okay, so basically it is directly given in your IS 456 based on the grade of steel you are proposing to use in your design. The value is actually given in a table in your IS 456. So basically for 250, 415 and 500 we have different values of limiting neutral axis. Okay, so once you have the limiting value of X limit by D, what you can do is that you just take the equation for your balance section, compute the minimum effective depth. So minimum effective depth can be again recomputed by, so here we have a minimum effective depth. Please note, here we have a effective depth, but we don't know whether that effective depth will be sufficient or not. Okay, this is where usually confusion come into picture, so please focus. Here we have an effective depth to start with, because to calculate the effective span and other thing, we require an effective depth. So for that, what we have done is that based on the control of deflection, we have just obtained a value for our effective depth, and we are not sure whether this effective depth will be sufficient to take up the load acting on the structure. So to ensure these things, we are again calculating the depth required. So right now we know what is the total moment acting on the structure. So we are just utilizing. So as an engineer, we know that we can permit to a maximum of a balance section. We always prefer a under reinforced section, but we can go up to a balance section. That is our maximum limit. So we are just focusing on the maximum permitted limit. That is by utilizing the relation corresponding to our balance section. We will substitute the bending moment, that design bending moment here, and right now we will be knowing the value of width, but we don't know the value of effective depth. We will be keeping this as a variable, D as a variable in this equation. We know the value of X limit by D calculated in step number 3. We also know the grade of concrete. So the only unknown in this equation will be our effective depth. So we will be getting a value of effective depth here. Then what we will do is that we will compare this depth with the assumed depth, or with the depth we have taken previously. Check if the effective depth provided in step 1 is sufficient based on this depth. So basically this is the minimum amount of depth actually required to produce this moment. So check whether the depth is larger or lesser with respect to this one, and make corrections accordingly. Okay, so this is what we do at this stage. And if it is okay, if this depth is actually okay, then what we can do is that we can compute the steel reinforcement. Okay, that will be done based on the equation corresponding to a under reinforced section. So we will be substituting the external design moment here, and we will be again finding out the AST with respect to the dimensions right now we have in our hand, that is B and D. Substitute it here and find out the value of AST. So once you get the value of AST, provide required number of bars. How you can find out the required number of bars? So you assume some diameter, maybe 20 or 16. You calculate the area of steel for that single cross section, divide the total AST by that, so that you will be getting some value. You just round it up and provide the number of reinforcement required. So after providing the reinforcement, say sometimes you will be getting it as say 3.25. So the number of bars required is 3.25. That is the minimum requirement. So what you have to do is that you have to provide 4 bars. So what will happen is that the amount of steel is now increased. So you have to again recalculate the capacity of that section from this equation. So now the AST that should be substituted is the revised AST. That is, from here the minimum AST is obtained as 3.25 bars. So you have provided 4 bars so that the AST is increased. So you calculate 4 times the area of cross section of the assumed diameter and substitute it here, and again recalculate the value of moment of resistance. Now what you have to do is that you just compare this moment of resistance with that of a balanced section, that is the critical moment of resistance. If the moment of resistance obtained here is less than critical moment of resistance, that means your section is a under reinforced section, so it is safe. So if mu is equal to that MU limit, that is again a balance section. If it is less than MU limit, it is a under reinforced section. So in both these cases, your design will be safe. If it is not safe, what you have to do is that you have to repeat the entire procedure by revising your depth. Okay, so you have to revise your cross section. That is the only possibility there. If it is safe, you can actually proceed to next part, that is the shear design. And we already know what is the procedure that should be adopted for performing the shear design. So in this stage, you have to actually perform the shear design. Then you have to perform all the checks, that is for minimum reinforcement in the tension zone, maximum reinforcement in the tension zone, minimum shear reinforcements, maximum shear reinforcements, and regarding the spacings. We have different checks. You have to perform all these checks. Also regarding the deflection. Anyway, deflection will be safe since we have assumed the L by D ratio as suggested by the control of deflection. So once you complete all these cases, you have to produce the detailing. That is, you have to provide the final drawing. So basically, to conclude, the complete design will be a combination of what you have learned in your first module and the second module, plus some checks and the detailing. So this will complete the design of a single beam.